Welcome to the Bombardier Q400 virtual flight deck. Today, we are going to completely master a really critical part of this aircraft, the ATA-21 air conditioning and pressurization systems. Whether you're a pilot, a student, or just a total aviation geek, this explainer is designed to demystify exactly how we breathe, stay comfortable, and, well, survive up at 25,000 feet. Let's dive right in.
Here is our flight plan for today. 1. AC general and panel controls. 2. ECU flow and temperature control. 3. Air distribution and non-normal. 4. Avionics cooling and ram air. 5. Pressurization controls and indicators. And 6. The 4 pressurization modes. To make this complex system super easy to memorize, we are going to follow a strict linear cockpit-to-cabin flow, and we won't skip a single step.
Section 1. AC General and Panel Controls. Let's start right up front at the controls to set a baseline for how we condition the air.
At the very heart of our environmental control system are the air conditioning packs. Basically, these take incredibly hot bleed air from the engines or the APU and condition it for the perfect temperature and humidity. Now, to effortlessly remember the core architecture here, just use the rule of twos. It's super simple. The Q400 has 2 packs, 2 air cycle machines, 2 heat exchangers, and 2 engines. This dual setup gives us the absolute crucial redundancy we need.
Moving over to your pack controls, you're going to use the OMA trick. That's OMA for off, man, and auto. Off simply shuts the air cycle machine down. But switch it over to man or auto, and you begin supplying conditioned air while modulating the bypass valve. Right next to that is your bleed control. For bleed airflow, you've got to remember the MMM rule, min, norm, max. And here is a huge takeaway. You can never, ever forget that min is the absolute only selection permitted for takeoff. Norm and max are great for modulating flow during other phases of flight, but for takeoff, min is the law. Section 2, ECU flow and temperature control. We know how to turn it on, but let's see how the electronic control unit actually manages this airflow.
So the ECU acts as the brain of our system, using both a digital channel and an analog backup, but they are totally different beasts. The digital channel does all the heavy lifting, modulating the nacelle shutoff valves for perfect flow. The analog backup? Well, it actually has zero control over the pack flow control shutoff valve. In fact, if digital power fails, that analog backup just slams the valve pneumatically closed.
Now, when you are manually targeting full cool, you need to memorize the 2.8 ICE rule. Basically, 2.8 degrees Celsius is the absolute minimum temperature permitted. Why? Because dipping below that literally invites dangerous ice to form on the condenser, and you definitely don't want to block your airflow.
Now, if you're just cruising in auto mode, the ECU uses zone sensors to maintain a really strict comfort zone. We're talking 15 degrees Celsius for full cool, up to 27 degrees Celsius for full warm. It keeps everybody on board perfectly comfortable.
Section 3. Air distribution and non-normal. We've conditioned the air, so let's distribute it through the cabin and flight compartment. Once that air leaves the packs, a distribution damper splits it up. To memorize these splits, just remember basic physics. Heat falls, cool rises. In heating mode, 70% of that warm air drops right down to the lower dado panels. But switch to cooling and bam, 70% of that cool air shoots up to the upper gaspers. And standard mode, it's just a clean 50-50 split.
But hey, things go wrong, right? If an overheat happens, the digital channel is going to automatically shut off the affected turbine and throw one of 4 very specific caution lights at you. You'll see flight compartment duct hot, cabin duct hot, cabin pack hot, or flight compartment pack hot. It's the system's way of screaming for your attention.
Section 4. Avionics cooling and ram air. Passenger comfort is great, but protecting our flight instruments is absolutely critical.
For avionics cooling, you have exactly 3 extraction fans. But here is the golden rule for dispatch. 3 fans, 2 to dispatch. You only need 2 of them up and running to legally take off.
Let's look at how they perform as power degrades. Normally, with the main DC bus active, fans 1 and 2 are blasting at high speed. If one fails, fan 3 automatically jumps in. But if things go really south and you're down to just battery power, fan 1 is your lone survivor. It runs on low speed, providing the bare minimum cooling to keep your LCD screens alive.
Section 5. Pressurization controls and indicators. Next, let's seal up the tube and check out the controls keeping this bird pressurized.
You've got 2 main players here,
The aft outflow valve is your electrically operated, automated primary workhorse. It does the daily grind. That contrasts sharply with the forward safety valve, which is entirely mechanically operated. That forward valve is your manual backup and your go-to for emergency smoke removal.
When you're forced into manual or emergency modes, your eyes need to be glued, and I mean glued, to three indicators: differential pressure in PSI, cabin altitude in feet, and rate of change. You have to know exactly what the pressure inside that tube is doing.
Section 6. The 4 pressurization modes. Let's see how the cabin pressure controller actually utilizes these valves.
To recall your 4 modes in a snap, just use the mnemonic AMID: automatic, manual, emergency, and dump. Automatic is your standard day-to-day. Manual lets you drive the aft valve. Emergency uses the forward valve. And dump, that fully opens the aft valve to dump the pressure immediately.
In automatic mode, the system is brilliant. It actually pre-pressurizes the cabin to 400 feet below takeoff altitude before you even roll, and it uses the 10/5000 abort rule. It smartly holds that takeoff altitude for 10 minutes or up to 5,000 feet. If you have an emergency and have to quickly return to the runway, this logic prevents rapid, painful pressure bumps in your passengers' ears.
As you climb, you need to know your limits. Your absolute maximum differential pressure limit is 5.46 psi. It's this exact structural limit that seamlessly maintains an 8,000-foot cabin while you are cruising way up at 25,000 feet.
Okay, we've covered normal and backup ops. But what if both AC packs fail completely? What happens when you lose all pressurization?
In this extreme scenario, you rely entirely on emergency ram air ventilation. Outside air forcefully enters through the dorsal NACA vent, ventilates the cabin, and exhausts right out the forward safety valve. It keeps everyone breathing. But I want to leave you with this final thought. During a high-stress, unpressurized emergency, with alarms absolutely blaring, are you truly prepared to manually manage that forward outflow valve while safely flying the Q400? Knowing this stuff isn't just about passing a check ride, it's about surviving that exact moment. Thanks for hanging out with me for this explainer, and keep studying.